Hello everyone, welcome again. So in this video we are going to solve and continue the problems which we are doing in the last session. So our next problem is, which is problem 4 I suppose. Evaluate so in this one we are trying to evaluate x square into cos square x dx, and we start as usual. Denote the integral by I, and we can see I equals to x square cos square x dx, and as in previous examples we can again see this is an example where we have algebraic function and a trigonometric function multiplied together, so we are obviously going to need the IBP. So set first function equals to x square, second function as cos square x. Right, so we want to see if this kind of a approach works in our favor or not, because more often than not this kind of approach works, but then again we need to experiment. So what I'm trying to do here is not to solve the problem directly, but I'm trying to think in terms of how you guys are going to think, because obviously what you have learned till date is to have the algebraic function as the first function, trigonometric as the second, and then do IBP. Right, so that's what I'm trying to do. Okay, so the next step would be to do the IBP. Let's do the IBP. Okay, I equals to x square into cos square x dx, and by IBP, so I will write it down in the end. X square into cos square x integration minus d dx of x square is just 2x, and integration of cos square x dx. This is by IBP. Okay, now we need to find out what this integral actually evaluates to. So set j equals to integral of cos square x dx. Now we find that cos square x is basically integral of 1 plus cos 2x by 2 dx. So this is a formula from double angles in trigonometry, which you already have learnt in 11th, and we are going to use it. We are going to first separate those two integrals as half dx plus 1 by 2 into cos 2x dx, and this would give us x by 2 plus 1 by 4 sine of 4x plus c. Right, so this is our required integral, and we would not need the c while evaluating that. So coming back to the original integral, we have I equals to, so let me just write down what we had before, x square into cos square x dx so now I'm going to put the value of cos square x dx, and I'll explain after I solve the problem. Here you can see that the integral of minus x squared dx is just minus x cubed by 3. So what we'll write is this, minus x cubed by 3. The x square sine into 4x by 4 term remains as it is, and what we are left with is this integral x into sine 4x by 2 dx, which let us rename as capital P, and we shall evaluate it below. Now, as before, this is the algebraic function, this is the trigonometric function. So by IBP, what we get is this. So this is the answer to the value of P, and therefore if you can put it back, the answer would be so I would be equal to x cubed by 2 minus x cubed by 3 is just x cubed by 6 plus we have x square sine 4x by 4 and we had a minus P, so rather what we will have is this. Plus C, which is the answer. So this generally necessitates our value for the function, and we understand that this is how we solve certain problems which might require twice to be solved, or integration by parts was applied twice here. It might be a little bit of a longer problem, but then again indefinite integrals in its hardest forms are like this only, so you have to be very much habituated in order to solve this kind of problems. Okay, so what we are trying to do here is that in this integral, the next one that I'm going to do would be something of a definite integral kind, so we need to have a little bit of introduction of definite integrals in order to do the next problem. So let us do that. The heading is definite integrals. Now, so as we have learned in indefinite integrals that every time we are going to integrate a function, so let us say we are integrating fx of dx, what we get in back is some function g of x plus c, right? And this g of x is called the antiderivative of f of x, right? Because when you take the derivative of g of x, you get is f dash x, that is g dash of x should be equal to fx. Okay, but in definite integrals what we have is something we call the lower limit and the upper limit. So if integral of f of x dx is equals to g of x plus c, then when you have the limits, the same thing goes like this. So let us say you have from 2 to 3 f of x dx, so where 2 is the lower limit and 3 is the upper limit. This means that we have this integrates to g of x plus c. So what we do is we first put in the value of the upper limit in the value of the integrand, so which is g of 3 plus c, and we subtract from it after putting the value in the lower limit, which is g of 2 plus c. And as you can see, the constant c's get cancelled off, and what we get is g of 3 minus g of 2, which is the answer. And it's the answer without a constant, so it's a definite answer, right? So just to give an example, integral of x squared dx from 1 to 2. So firstly we know integral of x squared dx is just equals to x cubed by 3 plus c, right? Using this fact, what we can do is we can write x cubed by 3 plus c. This is the integrand and the limits are 1 to 2. So put in 2, we get 2 cubed by 3 plus c, and put in 1, we get 1 cubed by 3 plus c. So what we have is 8 by 3 plus c minus 1 by 3 minus c. The c's get again cancelled off, and it will always get cancelled off in case of definite integrals, and the answer would be 7 by 3. So as you can see, this represents a number, right? This represents a number which is 7 by 3. So what does it exactly mean? It means that something like this. So suppose this is our axis and the function is y equals to x square. Okay, so this is a parabola like this. Okay, this is a parabola like this, and this parabola has, this is basically y equals to x square. So let us say this is the x-axis and this is the y-axis, and let us say this is x equals to 1, let us say this is x equals to 2. So what it does is it finds out the area between 1 to 2. So what it does is it finds out the area between this portion, and this area is 7 by 3, because what we did was basically integrated 1 to 2 x squared dx, right? And it came out as 7 by 3. So as you can see, it helps us to calculate the area. The definite integral is a form of area in graph. So every graph problem where an area is due can be modeled as a definite integral problem, and vice versa. That's how it works, right? So this definitely gives us an idea. So let us do one more problem, and there are lots of properties of definite integration that needs to be learned, and there are lots of problems, lots of techniques that need to be learned. So let us first complete one of them. So similarly, for this problem, we know the antiderivative for e to the power x is just e to the power x itself, right? So you can write it directly as e to the power x, and the limits from 100 to 1. So be comfortable with the limits first. So you put in 100 in terms of x, e to the power 100, and then you put in 1. So the answer is e to the power 100 minus e, right? Similarly, if you again have x squared dx, you know that the antiderivative is just x cubed by 3, right? From 0 to 1. Then you put in 1 by 3 minus 1 minus 0 by 3. So you just put in the values, no need to write the constant c, and you can write it directly like this. This is 1 by 3, right? So in general, for this kind of an integral, in general, zero to 1 x to the power n dx is equal to 1 by n plus 1, where obviously n not equals to minus 1, because otherwise the integral is just log of x, and log of 1 minus log of 0 is not defined. Okay, that is, notice that 0 to 1 1 by x dx diverges to positive infinity, and you will see why in the later chapters when I will try to explain you with the graphs of why 1 by x dx diverges to infinity, and this has relation with the harmonic series too, which also diverges. So anyways, this is the basic introduction for definite integrals. Because we already know about indefinite integrals, we can start off with some stuff of basic integrals now. So in the next chapter we shall also cover about definite integrals more, and that would be the beginning of definite integrals, and 2-3 videos or 2-3 lectures would be enough to cover the portion we require in order to start continuous random variables. So thank you for watching the video, and please do check in the link in the description about the Breatter Maths app, where all these video lectures and all the notes and theory and everything else is provided. So do check it out. Thank you.